Hello friends, in today's lecture we will talk about videos as they form the major component of multimedia applications. Since the first silent movie flickered to life, people have been fascinated with motion pictures. To this day, motion video is the element of multimedia that firmly holds the student's interest in a computer based learning project. Digital video is the most engaging of multimedia venues, and it is a powerful tool for bringing computer users closer to the real world. It is also an excellent method for delivering multimedia to television audience. With video elements in your project, you can effectively present your messages and reinforce your story, and viewers tend to retain more of what they see. But take care, video that is not well produced can degrade your presentation. The major components of video which we shall be discussing later in this lecture are use of digital video in multimedia, analog and digital technologies, digital video containers and codec, and finally shooting and editing videos for multimedia. Carefully planned, well executed video clips can make a dramatic difference in a multimedia project. Before deciding whether to add video to your project, it is essential to have an understanding of the medium, its limitations and its cost. This lecture provides a foundation to help you understand how video works, the different formats and standards for recording and playing video, and the differences between computer and television video. The equipment needed to shoot and edit videos as well as tips for adding video to your project will also be discussed. Working with multimedia video today can be like a desert camping trip. You may pitch your tent on comfortable high ground and find that overnight the shifting sands have buried both your approach and your investment. Of all the multimedia elements, video places the highest performance demand on your computer and its memory and storage. Consider that a high quality color still image on a computer screen could require as much as a megabyte or more of storage memory. Multiply this by 25, the number of times per second that the picture is replaced to provide the appearance of motion, and you would need at least 25 megabytes of storage to play your video for 1 second, more than 1.8 gigabytes of storage for a minute, and 108 gigabytes or more for an hour. Just moving all this picture data from computer memory to the screen at the rate would challenge the processing capabilities of a supercomputer. Some of the hottest and most arcane multimedia technologies and research efforts have dealt with compressing digital video image data into manageable streams of information. Compression and decompression using special software called a codec allows a massive amount of imagery to be squeezed into a comparatively small data file, which can still deliver a good viewing experience on the intended viewing platform during playback. If you control the delivery platform for your multimedia project, you can specify special hardware and software enhancements that will allow you to work with high definition, full motion video and sophisticated audio for high quality surround sound. Or you can design a project to meet a specific compression standard such as MPEG-2 for digital versatile disc playback or MPEG-4 for home video. You can install a super fast RAID system that will support high speed data transfer rates. You can include instructions in your authoring system that will spool video clips into RAM, ready for high speed playback before they need to play. Having control of the playback platform is always good, but it is seldom available in the real world. So, as you develop your video elements, you will need to make many choices and compromise based upon your assessment of the lowest common denominator playback platform where your project will be used. How video works and is displayed. When light reflected from an object passes through a video camera lens, that light is converted into an electronic signal by a special sensor called a charge coupled device. Top quality broadcast cameras and even camcorders may have as many as 3 CCDs, one for each color of the red, green and blue to enhance the resolution of the camera and the quality of the image. It's important to understand the difference between analog and digital video. Analog video has a resolution measured in the number of horizontal scan lines, but each of those lines represents continuous measurements of the color and brightness along the horizontal axis in a linear signal that is analogous to an audio signal. Digital video signals consist of a discrete color and brightness value for each pixel. Digitizing analog video involves reading the analog signal and breaking it into separate data packets. The process is similar to digitizing audio, except that with video, the vertical resolution is limited to the number of horizontal scan lines. For some multimedia projects, you may need to digitize legacy analog video. The following discussion will help you understand the differences between analog and digital video and the old and new standards for horizontal lines, aspect ratios and interlacing. Analog video. In an analog system, the output of the CCD is processed by the camera into 3 channels of color information and synchronization pulses, and the signals are recorded onto magnetic tape. There are several video standards for managing analog CCD output, each dealing with the amount of separation between the components. The more separation of the color information, the higher the quality of the image and the more expensive the equipment. If each channel of color information is transmitted as a separate signal on its own conductor, the signal output is called component, which is the preferred method for high quality and professional video work. Lower in quality is the signal that makes separate video, that is S-video, using 2 channels that carry luminance and chrominance information. The least separation and thus the lowest quality for a video signal is composite. When all the signals are mixed together and carried on a single cable as a composite of all the 3 color channels and the sync signal, the composite signal yields less precise color definition, which cannot be manipulated or color corrected as much as S-video or component signals. The analog video and audio signals are written to tape by a spinning recording head that changes the local magnetic properties of the tape's surface in a series of long diagonal strips. Because the head is canted or tilted at a slight angle compared with the path of the tape, it follows a helical path which is called helical scan recording. As illustrated in figure, each strip represents information for one field of video frame. A single frame is made up of 2 fields that are interlaced. Audio is recorded on a separate straight line track at the top of the videotape. Although with some recording systems, sound is recorded helically between the video tracks. At the bottom of the tape is a control track containing the pulses used to regulate the speed of the recording head. Broadcast standards. 3 analog broadcast video standards are commonly in use around the world: NTSC, PAL and SECAM. In the United States, the NTSC standard has been phased out, replaced by the ATSC digital television standard. Because these standards and formats are not easily interchangeable, it is important to know where your multimedia project will be used. A video cassette recorded in the United States will not play on a television set in any European country, which uses either PAL or SECAM, even though the recording method and style of the cassette is same. Likewise, tapes recorded in European PAL or SECAM formats will not play back on an NTSC video cassette recorder. Each system is based on a different standard that defines the way information is encoded to produce the electronic signal that ultimately creates a television picture. Multi-format VCRs can play back all three standards, but typically cannot dub from one standard to another. Dubbing between standards still requires high-end specialized equipment. NTSC. The United States, Canada, Mexico, Japan, and many other countries used a system for broadcasting and displaying video that is based upon the specifications set forth by the 1952 National Television Standards Committee. These standards defined a method for encoding information into the electronic signal that ultimately created a television picture. As specified by the NTSC standard, a single frame of video was made up of 525 horizontal scan lines drawn onto the inside face of a phosphorus coated picture tube every 1/30th of a second by fast moving electronic beam. The drawing occurred so fast that your eye would perceive the image as stable. The electron beam actually made two passes as it drew a single video frame. First, it laid down all the odd numbered lines and then all the even numbered lines. Each of these passes, which happen at a rate of 60 per second or 60 hertz, painted a field, and the two fields were then combined to create a single frame at a rate of 30 frames per second. PAL, the phase alternate line system, was used in the United Kingdom, Western Europe, Australia, South Africa, China, India, and South America. PAL increased the screen resolution to 625 horizontal lines, but slowed the scan rate to 25 frames per second. As with NTSC, the even and odd lines were interlaced, each field taking 1/50th of a second to draw. SECAM, the sequential color and memory system, was used in France, Eastern Europe, the former USSR, and a few other countries. Although SECAM is a 625 line 50 Hz system, it differed greatly from both the NTSC and the PAL color systems in its basic technology and broadcast method. Often, however, TV sets sold in Europe utilized dual components and could handle both PAL and SECAM systems. Digital video. In digital systems, the output of the CCD is digitized by the camera into a sequence of single frames, and the video and the audio data are compressed before being written to a tape or digitally stored to a disk or flash memory in one of the several proprietary and competing formats. In 1995, Apple's FireWire technology was standardized as IEEE 1394, and Sony quickly adopted it for much of its digital camera line under the name iLink. FireWire and iLink and USB 3 cable connections allow a completely digital process from the camera's CCD to the hard disk of a computer, and camcorders store the video and sound data on an onboard digital tape, writable mini DVD, mini hard disk, or flash memory. HDTV. What started as the High Definition Television Initiative of the Federal Communications Commission in the 1980s changed first to the Advanced Television Initiative and then finished as the Digital Television Initiative by the time the FCC announced the change in 1996. This standard, which was slightly modified from both the Digital Television Standard and the Digital Audio Compression Standard, moved US television from an analog to digital standard. It also provided TV stations with sufficient bandwidth to present 4 or 5 standard television signals or one HDTV signal providing 1080 lines of resolution with the movie screen's 16:9 aspect ratio. This aspect ratio allows the viewing of CinemaScope and Panavision movies. There was contention between the broadcast and computer industries about whether to use interlacing or progressive scan technologies. The broadcast industry promulgated an ultra high resolution 1920-1080 interlaced format to become the cornerstone of the new generation of high end entertainment centers. But the computer industry wanted a 1280 into 720 progressive scan system for HDTV. While the 1080i format provides more pixels than the 720p standard, the refresh rates are quite different, but the computer people argue that the picture quality at 720i is superior and steady. So both formats have been included in the HDTV standard by the Advanced Television Systems Committee. Displays. Colored phosphors on a cathode ray tube screen glow red, green or blue when they are energized by an electronic beam. Because the intensity of the beam varies as it moves across the screen, some colors glow brighter than others. Finely tuned magnets around the picture tube aim the electrons precisely onto the phosphorus screen, while the intensity of the beam is varied according to the video signal. This is why you needed to keep speakers which have strong magnets in them away from a CRT screen. A strong external magnetic field can skew the electronic beam to one area of the screen and sometimes cause a permanent blotch that cannot be fixed by degaussing, an electronic process that readjusts the magnets that guide the electrons. Flat screen displays are old digital using either liquid crystal display or plasma technologies and have supplanted CRTs for computer use. Some professional video producers and studios, however, prefer CRTs to flat screen displays, claiming colors are brighter and more accurately reproduced. Full integration of digital video in cameras and on computers eliminates the analog television form of video from both multimedia production and the delivery platform. If your video camera generates a digital output signal, you can record your video direct to disk where it is ready for editing. If a video clip is stored as a data on the hard disk, CD-ROM, DVD or other mass storage devices, that clip can be played back on a computer's monitor without special hardware. Interlacing and progressive scan. The process of building a single frame from two fields is called interlacing, a technique that helps to prevent flicker on CRT screens. Computer monitors use a different progressive scan technology and draw the lines of an entire frame into a single pass without interlacing them and without flicker. In television, the electron beam actually makes two passes on the screen as it draws a single video frame, first laying down all the odd numbered lines, then all the even numbered lines as they are interlaced. On a computer monitor, lines are painted 1 pixel thick and are not interlaced. Single pixel lines displayed on a computer monitor look fine. On a television, these thin lines flicker brightly because they only appear in every other field. The term interlacing has a different meaning on the web, where it describes the progressive display of lines of pixels as image data is downloaded, giving the impression that the image is coming from blurry into focus as increasingly more data arrives. Most computers today provide video outputs to CRTs, LCDs or plasma monitors at greater than 1024 into 768 resolution. Table here describes the various aspect ratios and width oblique heights in pixels used by computer displays since IBM's VGA standard was adopted in 1987. In the realm of digital television displays, this table shows the most common screen resolutions. Overscan and the safe title area. It is common practice in the television industry to broadcast an image larger than will fit on a standard TV screen so that the edge of the image seen by a viewer is always bounded by the TV's physical frame. This is called overscan. In contrast, computer monitors display a smaller image on the monitor's picture tube called underscan, leaving a black border inside the frame. Consequently, when a digitized video image is displayed on a CRT, there is a border around the image, and when a computer screen is converted to video, the outer edge of the image will not fit on a TV screen. Only about 360 of the 480 lines of the computer screen will be visible. Video editing software often will show you the safe area while you are editing as shown. So friends, during this lecture we have talked about some of the basics of video, that is what analog and digital video is, what are the broadcast standards, over and underscan, HDTV, which display should be used for digital video, and finally what is progressive and interlace scanning. We shall continue our discussion on videos in next lecture, talking about digital video containers, the shooting and the editing process. So friends, that is it for today. See you in the next lecture. Thank you.